Hi friends, welcome back to a new session. See, in this session we will discuss about effect of non-linearity and saturation of magnetic core on the operation of transformer. Okay, let me take effect of non-linearity and saturation of magnetic core on the operation of transformer. See, generally, if you neglect non-linearities and saturation of magnetic core on the operation of transformer, IMU and flux, core flux and magnetic current will be in phase with each other. Suppose now we are considering that effect of non-linearities and saturation we are considering here. So because of that, what will happen, we'll see. Before that, first of all, let us discuss ideal case. Ideal case means what I can say. If you want me to draw shape of pi versus I mu graph, if you increase I mu value, flux will increase. If you increase I mu value, flux will increase. If you increase I mu value, flux will increase. That means there is no saturation. If you increase I mu value to infinite, flux also will go to infinite. If you increase I mu value to infinite, flux also will go to infinite. That means what? No saturation. Ideally, I can say that no saturation. And whenever you increase the current value, at that time whenever flux is increased, that path can be called as magnetation path. Okay. Now, if you reduce I mu value, flux will reduce in the same direction in which flux was increased. If you reduce I mu value, flux will reduce, no doubt. But it will reduce the same path in which it was increased. That means demagnetization and magnetization, they will coincide with each other. If they are coinciding with each other, I can say that I don't have any non-linearity. Okay, so no saturation and no non-linearity. No saturation and no non-linearity. Is that clear? Okay, so no saturation, no non-linearity. Here, let me have some observations here. Excuse me. Please tell me. I want some observations here. Okay. So tell me, current maximum point, flux maximum point occurs simultaneously or does not occur simultaneously? Just see their figure and tell me. Suppose if I increase I mu this much, flux is this much. If I increase current this much, flux will this much. If you increase I mu this much, flux will this much. That means maximum point of current and maximum point of flux coincides with each other. So let me write that point here. Current maximum point, comma, flux maximum point occurs simultaneously. And second point, if you reduce current, flux is reducing the same path in which it was increased. And here, if I reduce I mu to 0, flux also coming to 0. That means this is the current 0 point and this is only your flux 0 point. Let me write here. This is the current 0 point and this only I can say that the flux 0 point also. That means, can I write like this? Current 0 point, comma, flux 0 point occurs simultaneously. These are the two observations you have to remember. Okay. So from which we can draw what is the shape of I mu waveform required for getting a sinusoidal shape of a flux comma EMF waveform. Okay, this is ideal case. Now please tell me, practically, practical case. So if you want me to draw shape of pi versus I mu graph, pi versus I mu, if you increase current, flux increases like this, and if you reduce, if you are increasing current, flux increases like this, and it will enter into saturation. Okay, so actually let me draw pi, first of all pi curve, then we can explain. So if you increase I mu value, flux will increase like this. This is nothing but the path of magnetization. So here it will enter into saturation. It will enter into saturation. This is plus I mu m. Corresponding to this, you are getting here plus pi saturation. If you reduce current after this instant, see, I just include here saturation into account, because after this instant, if you increase current also, there is no increment in flux value, because core enters in saturation. So your maximum value is plus pi sat only. That means here I am just taking saturation into account. Previously I had not taken saturation. Now I am just taking saturation into account. Next, if you reduce current, flux will reduce in a different path, not in the same path in which it was increased. Because of retentivity property, your magnetization and demagnetization will not coincide with each other. See, if you reduce I mu, flux is reducing. If you reduce I mu, flux is reducing. If current is coming to zero, flux is not equal to zero. Some flux is there. That flux can be called as residual flux. To be frank, positive residual flux. To make this a positive residual flux equal to zero, I have to apply negative current. If I apply negative current, then flux will come to zero here. Observe guys clearly. This is what I can say, flux 0 point. And this point nothing but current 0 point. Which one is coming first? Here obviously current 0 point, flux 0 point they are not occurring simultaneously. If you see in ideal case, current 0 point, flux 0 point occur simultaneously here. But here, current 0 point, flux 0 point does not occur simultaneously. You are increasing, first of all, you are increasing I mu, flux is increasing this direction, it will enter into saturation. So this is a plus I mu value, this is plus pi sat value. If you reduce current, flux will reduce. If you reduce current, flux will reduce. If you make current equal to zero, that means first it is coming to zero. First current point is coming to zero first. Current is coming to zero, but flux is not coming to zero. Some flux is there. That flux can be residual flux. To make this a positive residual flux equal to zero, I have to put negative current. Then this flux will come to zero here. That means this is the second case. After among this current 0 point, flux 0 point, which one is coming to zero first? Current 0 point is first. Then after that current flux 0 point is coming. That means current 0 point leads flux 0 point by an angle of alpha naught. So this can be taken as alpha naught. So saturation is there, and here magnetization, demagnetization, they are not coinciding with each other. If you see in ideal case, they are coinciding with each other. That's why I wrote here no non-linearity. But here magnetization, demagnetization are not coinciding with each other. So I can say that non-linearity is there. Non-linearity is there. And this is the current 0 point, and this is the flux 0 point. So I told you, for making this a positive residual flux equal to 0, I am applying negative current. So like this is the shape of pi a curve for one cycle of your I mu. I can call this one as the minus pi sat. I can call this one as the minus I mu m, and we can call this value as minus residual flux, minus residual flux. Okay. Now right. So let me give this observation. Whatever observation I wrote there, let me give some observations here. See here, previously I told current maximum point. Example corresponding to this I mu. This is the pi. This is the maximum value of your flux. Therefore, I wrote current maximum point, comma flux maximum point occurs simultaneously. Now tell me, in practical case, current maximum point, flux maximum point occurs simultaneously, does not occur simultaneously. So obviously they are occurring simultaneously. See, this is practically maximum value of your I mu. At this point, this is the practically maximum value of your flux. Pi sat and I mu, they are occurring simultaneously. You may think, sir, if I in a practical case, if I take I mu to infinite also, flux will not increase, it will enter saturation. Then how can you say that current maximum point and flux maximum point occur simultaneously? Practically, I cannot take I mu to infinite, no, generally. So practically, this is the maximum point of your I mu, this is the maximum point of your pi, that's it. So they are occurring simultaneously. So I can write here, current maximum point, comma, flux maximum point occurs, I can say occurs simultaneously. We can write here, since plus simium, comma, plus pi sat occurs at a time. Occurs, I can say at a time, or I can say occurs simultaneously at a time. And guys, very, very important. Second point is very, very important. Tell me, current 0 point, flux 0 point occur simultaneously? Yeah? No. Which one is coming to first? Which one is coming first? Current 0 point will come first. Then after some time, flux 0 point will come. Therefore, I can write here, current 0 point, comma, flux 0 point does not occur simultaneously. That is, I can say like this. Which one is leading? Current 0 point leads flux 0 point by an angle alpha naught. This alpha naught can be called as hysteretic angle, or I can say hysteresis angle in advance. Hysteresis angle of advance. It is current 0 point is advancing flux 0 point by angle of alpha naught. That's why he has given name hysteresis angle of advance. Okay, these are observations for practical case. Now I'll ask a simple question. Ideally or practically, guys, here we want some waveforms here. Please try to see. This is the shape of your first one. I'll take I mu, and the second one I'll take flux. Third one I'll take EMF. Similarly, in the practical case also, we'll have I mu, I want I mu waveform, and we want a flux waveform, and we want EMF waveform. Yeah, tell me. Ideally or practically, what is the shape of EMF waveform we require? Sinusoidal. So I need sinusoidal EMF waveform. Ideally, as well as practically, what is the shape of EMF waveform required? So I can say sinusoidal. We need a sinusoidal EMF waveform. Ideally or practically also, we need a sinusoidal EMF waveform we require. Now for that, what is the shape of your flux waveform? Generally, guys, E proportional d pi by dt one concept is there. Okay. Suppose here flux is, if I take sinusoidal, then only, if you differentiate sine wave, once again you'll get sine wave here, sine wave. That means if you want sinusoidal EMF waveform, flux waveform should be sinusoidal. So obviously, no doubt, I can say that if you take Lenz law into account, EMF lags flux by 90 degrees. But here I am not focusing about Lenz law. I am just thinking about the shape of your waveforms only. That's why simply I am just drawing a flux also. I am just drawing in phase with your EMF. Obviously, no doubt, angle will be there. But here I am just focusing on shape of your waveforms. That's why I am not taking angle into account. Suppose if you take angle into account, if it's a class starting point of your flux, so EMF lags flux 90 degrees, it will start from here, from this instant. Okay. But here we are not including Lenz law into account. I am just focusing what the shape of flux comma EMF waveforms will get. Okay. So this is what required flux waveform. Okay. So I want sinusoidal EMF waveform. For that, flux waveform should be sinusoidal. This waveform should be sinusoidal. Guys, practically also, I need for having a sinusoidal EMF waveform, flux required is also sinusoidal. Okay. Right. This is what I can do, shape of your flux waveform required for us. Okay. Nothing but sinusoidal once again, sinusoidal. Now tell me, if you want sinusoidal flux waveform comma sinusoidal EMF waveform in ideal case, what is the shape of your IMU waveform required? What is the shape of your IMU waveform required? Very simple. For drawing this IMU waveform, please try to see these observations. First observation, current maximum point, flux maximum occur simultaneously. This is the maximum point of your flux. So your current maximum point and flux maximum occur simultaneously. So obviously this is the maximum point of your current, and this is the maximum point of your negative max of your flux. This is the negative max of your current, and current 0 point comma flux 0 point occur simultaneously. This is the flux 0 point. So this should be coming current 0 point. Here flux 0 point, and here is current 0 point. Here flux 0 point. Here yes, current 0 point. So now observe clearly what is the shape of IMU waveform you are getting here. So obviously sinusoidal. Okay, sinusoidal. Please try to draw. This waveform should be almost it should be like a sinusoidal. Please try to draw sinusoidal waveform. Okay. Alright. So see, if you see this points, you can understand. So flux maximum point, current maximum occurs simultaneously. Flux 0 point, current 0 point occurs simultaneously. That means what? Yes, shape of your IMU also should be sinusoidal. This should be sinusoidal. So now conclusion, you can say that ideal case where saturation is not included, effect of non-linearity is not included, at that time I am asking what is the shape of your IMU waveform? So obviously sinusoidal, because I don't have any non-linearity, I don't have any saturation concept. So obviously shape of your IMU waveform is sinusoidal. So that I will get a sinusoidal flux waveform and a sinusoidal EMF waveform will get. Okay. To be frank, this is not only for ideal plus I can say air core transformer. Air core transformer means what here? Air core transformer. That's the transformer. Okay, air core transformer. Air core transformer means transformer core is made up of non-magnetic material. Non-magnetic Non-magnetic material. Non-magnetic material. Transformer core is made up of non-magnetic material. Observe guys clearly. Ideally, or for air core transformer, transformer core made up of non-magnetic material. For these two things also, non-linearity is not there, saturation is not there. Non-linearity not there means what? Linearity nature will be there. Okay. So ideal or air core transformer means no non-linearity. Once again I am writing here, no non-linearity and no saturation. So at that time, shape of your IMU waveform is what? Sinusoidal. I am saying sinusoidal. Simple. Okay. What about practical case? For knowing the shape of your IMU waveform, what you should know? You please try to see these observations and I can decide. Current maximum point, flux maximum occur simultaneously. That means this is the maximum point of your flux. So, and maximum point of your current also should coincide with the maximum point of your flux. And this is the maximum point of your flux should coincide with the maximum point of your current. What about second point? This is very, very important. This one will decide your waveform. Okay, shape. Current 0 point, flux 0 point does not occur simultaneously. That too, which one is leading? Current 0 point leads flux 0 point by an angle alpha naught. So this is flux 0 point and this is the current 0 point. They are not occurring simultaneously. To be frank, which one is leading? Current 0 point leads flux 0 point. This is flux 0 point. It is leading by angle how much? It is leading by an angle alpha naught. So similarly, this is what I can say, flux 0 point, current 0 point should lead. Therefore, this is your current 0 point. And I can say this is what your flux 0 point and current 0 point should be this one. Now please try to draw shape of your IMU waveform. So obviously please try to draw this shape of IMU waveform becomes like this. Shape of IMU waveform becomes like this. Nothing but non-sinusoidal. So, or I can say, or peaky waveform. What here? Peaky waveform. Okay. So guys, now let me conclude. In ideal or air core transformer, for having sinusoidal flux sinusoidal EMF waveform, so here there is no need of giving notes because everything is on the board. Please try to see here. If I want sinusoidal flux sinusoidal EMF waveform, IMU should be sinusoidal. Okay, IMU should be sinusoidal. Okay, and practically if you see, if you want sinusoidal EMF, sinusoidal flux waveform, what is the shape of IMU waveform? Non-sinusoidal. What is the meaning for that? You observe clearly. If it is sinusoidal, it is non-sinusoidal. That means what? Sinusoidal means what? If I don't want harmonics in a EMF flux waveform, if I don't want harmonics, no harmonics here, no harmonics, and here also harmonics should not be there, no harmonics. So obviously in current waveform, it's non-sinusoidal means what? Harmonics should be there. Harmonics are present here. That's the conclusion. That means if I don't want harmonics in a flux EMF waveform, harmonics should be there in a IMU waveform. Previously I told one statement. If I want sinusoidal flux EMF waveform, IMU waveform should not be sinusoidal, it should be non-sinusoidal, it should be peaky waveform. Same statement only I am just saying in terms of harmonics. If I want sinusoidal means what? If I want no harmonics in a flux EMF waveform, harmonics should be there in a IMU waveform. Simple thing I am saying. Harmonics should be there in a IMU waveform. Okay. And here you should understand one thing. Here you should understand a small thing here. Harmonics. Okay, harmonics. Generally, Let me take a fundamental waveform 1. It's nothing but fundamental. And in addition to these, so many harmonics are there. Let me take 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. These are the harmonics. I told you already. Okay. If waveform is symmetrical about x-axis, if waveform is symmetrical about x-axis, according to Fourier transformation, if waveform is symmetrical about x-axis, according to Fourier transforms, even harmonics will cancel with each other. If waveform is symmetrical about x-axis means what? Same magnitude out of phase. If it is like that, even will cancel with each other means what? It can cancel 2, 4, 6, 8, 10, 12, 14 and so on. So next this is about fundamental. And if I cancel test, I mean even harmonics, what are the odd harmonics we are having? 3, 5, 7, 9, 11, 13 and so on. Out of these harmonics can be called as odd harmonics. Out of these odd harmonics, what is the dominant harmonic which will disturb your waveform shape, which is having capacity to disturb the waveform shape? Nothing but third harmonic. It will be around 30 to 40%. Out of 100% harmonic, 30% to 40% contribution is because of third harmonic only. Okay. So this third harmonic is nothing but most dominant. Since I can say that it will be around 30 to 40%. That means instead of saying every time harmonics, tell me approximately in place of harmonics you can simply say third harmonic. That means if we don't want the third harmonic in EMF waveform, that means if you are able to eliminate third harmonic, shape of your EMF waveform becomes almost all sinusoidal, because it is around 30 to 40%, no? So that means instead of every time there is no need to say harmonics like that. In place of harmonics, let me take a most dominant harmonic, nothing but third harmonic we will take into account. Okay. So if I don't want third harmonic here, flux waveform should not contain third harmonic. So IM waveform should contain a third harmonic. So let me write here. If we don't want no third harmonic, if we don't want third harmonic means what? If there is no third harmonic here also no third harmonic, but whereas in current waveform third harmonic should be there. This point is very important here. These points are very important. These points. See, conclusion please. Observe, try to understand. If a third harmonic is not there in the flux-cum EMF waveforms, that third harmonic is there in the IMU waveform. Suppose if I ask you reverse example, if third harmonic is there in the flux-cum EMF waveform, is there means in IMU waveform third harmonic will not be there. Is it clear? If it is not here, it will be here. If it is not here, it will be here. That's a simple logic. Okay. So what is the conclusion I can give? Last. So ultimately, what is the shape of flux comma EMF waveforms you require? Flux comma EMF waveforms you require, I'm asking. Sinusoidal. That means you are saying indirectly, I don't want harmonics in flux comma EMF waveforms. That means you are saying indirectly, I don't want third harmonic in a flux comma EMF waveforms. That means you are saying, I need third harmonic current in IMU waveform. That is the conclusion. First note down this. After that, I'll give that conclusion. Okay. Right. Now please try to see your classroom workbook, question number 31. There one question was asked regarding air core transformer. Please try to see that question number 31. Just study. You can understand what is the answer for that question. Question number 31 I said in your classroom workbook. Please try to study. He simply just you can see afterwards. See, very simple thing he is asking. He is asking indirectly that question. If you study, you can understand. He is asking what is the shape of I mu for air core transformer. For air core transformer, he is asking shape of your I mu. So very simple. Air core transformer does not have any non-linearity in saturation. So for air core transformer, shape of I mu means it will simply follow flux waveform. So flux waveform is sinusoidal. Shape of your I mu waveform is also sinusoidal. Sinusoidal waveform is the answer for that question number 31. Option C is the answer. Okay. Now please. Now let me conclude here. Excuse me. Let me conclude. So what you said ultimately for practical transformer, what is the conclusion? If I want sinusoidal flux gamma EMF waveform, that means if I don't want third harmonic in a flux gamma EMF waveform, third harmonic should be there in I mu waveform. That's the conclusion you got. That's the conclusion, right? That's the conclusion. So let me write same conclusion as a note here. Please try to note down that note. I'm just giving corresponding to this waveform. I'm just giving conclusion. See, for making flux gamma EMF waveforms, free from third harmonic. Free from third harmonic means what? If you don't want to third harmonic in a flux gamma EMF waveform, that's the meaning. For making flux gamma EMF waveform free from third harmonic, okay, third harmonic should present in I mu waveform. So if I don't want third harmonic in flux gamma EMF waveforms, third harmonic should be there in I mu waveform. The same thing what I just wrote in a sentence formation. Okay, this is the conclusion number 1. So indirectly, or I can say, that means you want to say that I need third harmonic in a current waveform. You are saying, what is the conclusion? We need third harmonic current waveform in a I mu waveform. That means there should be path. If I say that I need third harmonic, I need third harmonic current means, what's the meaning? That means there should be path for third harmonic currents from phase to phase, from R phase to Y phase, R phase to B phase, Y phase to B phase, B phase to R phase, like that. Or I can say A phase to B phase, B phase to C phase, C phase to A phase, like that. So there should be path for third harmonic currents from phase to phase or line to line. Then only I can say that yes, third harmonic current is there in I mu waveform. So then only I can say that flux gamma EMF waveforms will be free from third harmonics. Is it clear? So that's why same statement I'm just writing in a different way. Or I can say there should be path for third harmonic currents from phase to phase or line to line. That means there should be path for third harmonic currents from phase to phase or line to line. Okay, please write this one. next in the next session we'll discuss for any, not only for third harmonic current, any current, if it wants to flow from one phase to another phase or one line to another line, it has to satisfy one property. We'll see what is that property, whether that property was satisfied by these third harmonic currents or not, we'll see. If it is satisfied, very good, no problem. If it is not satisfied, then also at any cost we have to provide path for these harmonic currents from phase to phase or line to line. Then only your IME become peaky. Then only flux gamma EMF waveforms becomes a sinusoidal. Okay, so that we'll see in the next session how we have to provide path for third harmonic currents. Whether third harmonic current, if it wants to flow any current from one phase to other phase, I told you already it has to satisfy one property. But these currents are satisfying that property or not, we'll see. Okay, if it is not satisfied, how we have to provide a path for these harmonic currents so that we can make flux gamma EMF waveforms sinusoidal. Okay, that we'll see in next session. Just note on this.